Chemical Engineering Division Board. Due to sudden important work, Dr. Hemant Thakurji, Honorable President, is not available to join this meeting, as well as Dr. Ranganath, Chairman Kate, as well as Dr. Silpa Tripathi, Chairperson, Chemical Engineering Division Board, in her absence here, will start this meeting. Let me welcome and acknowledge Dr. Jitendra Saxena, In-charge Director Technical, Mr. King Sung Sen, Assistant Director Technical, for providing all technical facilities and support for approval procedure. It's my immense pleasure to welcome the eminent panelist of today's webinar, Mr. Manish Joshi. He is petrochemical professional specialized in polyolefin production. We have another panelist, Mr. Manoj Motiani, petrochemical professional who is specialized in olefin production. This eminent speaker will share their knowledge and experience in that domain. Today's moderator cum secretary of IEI Southwest Local Chapter Surat, Professor Ketan Panchal, Assistant Professor, Mechanical Division, South SS Gandhi Engineering College. And my dear participant, all are wholeheartedly welcome to attend this event. This particularly topic named Circularity, Challenges and Opportunity in the World of Plastic. So all of us know that even government banned the single-use plastic policy, and if I remember, it's from 1st July 2022. So plastic is a very big issue, and for that we have very renowned expert in this domain. They will share their knowledge. So we already late, not wasting the time. I'm proceeding hand over to moderator. He can introduce our speaker so we can proceed accordingly. Thank you, everyone.
Thank you, sir. Namaskar to everyone. I warmly welcome my two panelists, Mr. Manoj and Mr. Manish, my good friend. Let me have an opportunity to introduce both of our eminent speaker today. Dear friends, Mr. Manish Joshi is having a wide experience of 22 years in the field of polypropylene. He has worked with the leading petrochemical companies in India and as well as abroad, like Reliance, SABIC, Opel, and Aditya Birla. Mr. Manish was also involved in design, construction, startup, and cooperation of polypropylene unit. In addition to these, as he is having a bachelor degree in chemical engineering, is an accredited energy auditor from the Bureau of Energy and Energy Efficiency. Obviously, he is our part of IEI fellow member, registered chartered engineer, and presently working as a manufacturing technology manager with a USA-based company, Ms. W.R. Grace, and responsible for supporting the clients for their upcoming Unipol PP technology plants across the globe. I heartily welcome you, Mr. Manish, and we are looking forward for the great interaction with the participant. Let me have an opportunity to introduce our second eminent speaker, Mr. Manoj Motiani. Hello. Mr. Manoj is also a chemical engineer and executive alumni of IIM Lucknow with around 24 years of experience in the field of petrochemicals, specifically in ethylene production. He's also worked with the different MNCs like Reliance, SABIC, Opel in the past. Mr. Manoj has handled many functions like production and technical services in addition to different project phases of ethylene cracker plants also. He's also a fellow member of Institutions of Engineers India, currently works with the Linde Engineering India as AGM, and associated with engineering activities of petrochemical plants. We are lucky to have you as a speaker, Manojji. Now, without spending a single minute, I welcome Mr. Manish Joshi to start their presentation. Thank you. one more suggestion or instruction to participants, please. If you have any doubt during the session, kindly put in your question answer session. We would like to include all the questions from your side at the end of our speaker session. Thank you. Mr. Manish, over to you.
Yeah, thank you very much, Panchalji. Thank you very much, the eminent panel of IEI. And I would like to, extend my thanks on behalf of myself and Manoj for giving the opportunity to present ourselves. I believe the audio is okay. I am audible. So I'll start sharing the presentation and we will go forward.
Yes, you are perfectly audible.
Yeah, so the presentation is visible, sir?
Yes, visible.
Can you kindly confirm on that?
It is visible. Kindly go for the slideshow, full slideshow.
Yeah, correct. So I think now I'm in full slideshow.
Yeah, that is perfectly okay.
So first of all, I wish to, have warm welcome to the audience and all the eminent speakers, and at the same time, extend, the words of apologies for the glitch we had towards the start of the session. The world is very big, the technological issues come in and out, but then I think we resolved in time, and thanks for the team who helped resolving it, as soon as possible. So with this, I will start, the topic today is circularity, challenges and opportunities in the world of plastics. So let me, brief with the agenda today. So I will start with the icebreaker. So icebreaker is nothing but it is a kind of motivational story to aggregate, the attention of everybody who is part of this session. So once the thoughts are channelized, once we are aligned with our, brain and heart, it is basically, good to understand the subject later. Then I'll talk about the context setting on the circularity. Then we'll talk about the plastics, whether it is a blazing or trouble. We talked about, plastic is a trouble, but then we will try to see if plastic is a trouble or the plastic waste is a trouble. Okay, we will try to look into that. Then plastic footprints in the world as well as in India. We will talk about the understanding the linearity versus circularity, the way we use plastic today and the way we are trying to foresee the use of plastic in future. Then turning the ambitions into design of polyolefins. Then we will talk about rethinking, sourcing of alternate methods for recycling, the opportunities and challenges in this field, and finally, the takeaways. So I talked about the icebreaker, right? So we are all engineers, and being engineers, day in and out, we talk about the units, right? Every day. And many times, I mean, since my college time, I also remember, at times, even in the examination paper, I used to do, some mistake in the unit conversion. So how much a unit conversion error can cost you? That is the title or the topic I want to, put upfront in front of the audience today. So many of us may be aware of this incident. It is widely available on the public domain web page. So if you remember the Mars Climate Orbiter incident from 1999, very famous in the history. So basically, it is a mission of Mars, NASA, and Mars Climate Orbiter. As we know, 1 minute, I'll take some time to just readjust the slide. Yeah, so basically NASA has a project somewhere in 1998, and they built a Mars Climate Orbiter, and it cost around 125 million US dollar. The weight was around 340 kilogram. It was a robotic space probe, and it was launched by NASA on 11 December 1998. The purpose of this project was to study the Martian climate, Martian atmosphere, and the surface changes. So after 286 days of long journey, and 500 million miles of the distance covered. So just to give the brief what this 500 million miles is about. So it is more than 13,000 times we circle around the Earth. So equivalent distance is traveled to reach to the Earth. To the Mars. And finally, it reached on September 23, 1999 on the Martian atmosphere. And basically, the system activated to push the probe down onto the orbit of the Mars. The engine fired, but the spacecraft came very close to the surface of the Mars. And then it should have been, activated much before, but then it could not activate at that time, and finally it got very close to the Martian surface, and finally the system activated. So basically what happened is it malfunctioned, the spacecraft propulsion system overheated, and it was disabled as a climate orbiter, and finally it crashed. So basically, the mission is failed. But this failed mission has given a very big learning for the mankind. So what is the learning? Let's see that. So it is very interesting to see what went wrong here. So basically, Jet Propulsion Laboratory of NASA used the metric system. So we see that is millimeter, centimeter, and meter system. The probe supplier, who is a third party, and Lockheed Martin is the name of the supplier, and they use the English system. So English system is all about inches, feet, and pounds. So there was a conversion error in the programming of the probe, and the differences in estimating the landing elevation. So finally, physics perfectly worked, but the unit system incorporation into the program was failed, and the mission was failed drastically. So what are the lessons learned?
तो हमने ऑलरेडी शायद मेल भेजा हुआ था, तो हमने सेंड कर दिया, तो जो भी इंटरेस्टेड हो के वो कर देंगे पार्टिसिपेशन. ठीक है, अभी एक मीटिंग है, वो बाद में देखते हैं.
Yeah, so I think I hear some conversation. I don't know. Can you please mute your mic? So what are the lessons learned here? So some of the prominent people or the leaders who involved in the project, they finally spoke about the learning out of this project. So John Pike was one of them, the space policy director. He said, it is going to be a cautionary tale until the end of the time. It's a very, very big learning for the mankind. Another gentleman said, this was not a failure of Lockheed Martin. It is not a failure of the third party who supplied the probe. It was the system failure to recognize and correct an error that should have been caught. And this is an end-to-end process problem. Yeah, so it is not a particular problem. So as an engineer, I think there is a big learning involved here. So with that, I would also like to, quote a couple of more examples, which are kind of, learning, or we can say a surprise history. Probably many of us may like to know about it. Another incident is 1983, very famous Air Canada Boeing 767 incident. Yeah, in the mid-air, basically the fuel got exhausted, and finally they discovered that the airline recently changed over the system of measurement, and it ended up in exhaustion of the fuel mid-air. History sometimes gives surprise, and they are pleasant surprise as well. So basically, we know Columbus discovered America, right? But the target of Columbus to come to India, but the problem happened in the unit conversion again. Yeah. He landed up into the Bahamas of America rather than it should have been, Asia on October 12th, 1492. So with this, let us change the gear and come to the topic today. I would like to start with a famous quote. We don't inherit the earth from our ancestors. It is something we borrow it from our children. And this was the theme for World Environment Day 2022 Global Campaign Only One Earth. So this thing calls for transformative changes to policies and choices to enable cleaner, greener, and sustainable living in the harmony with the nature. It focuses on need to live sustainably in harmony with nature and our possibilities for shifting to a greener lifestyle through both policies and individual choices. So we talk about this in the slides later. This is the slide. Basically, I try to compile, some of the headlines from the global as well as the national newspapers, some cutouts. So if you see, all around it talks about the sustainability, circularity, and the policy changes and where the world is moving around. So United Nations agencies COP27 urge action to tackle the impact on plastic climate. We see EU Circular Economy Action Plan. The PM of India, Mr. Modi, says India is focusing on the green growth, green jobs, and urges promotion of the circular economy. There is an interesting fact. Before the government imposed lockdown of 2020, the amount of carbon dioxide in the atmosphere was the highest it had been in last 8 lakh years. So you can see, I mean, the changes we are, implying on the environment with the way the industrialization right now going on. India has set a target of net zero emission by 2070. And the PM of India also urges all ministers to promote circularity in all states, and this will also boost the campaign of solid waste management and freedom from the single-use plastic. From July 1, 2022, as Dr. Vagasia already highlighted, India has banned single-use plastic items that have been low in utility but are frequently littered around, such as plastic stoves and the gunny bags and all. So all the 28 states of India are now implied with this ban, and basically Uttarakhand is the last to join into the club in April this year. The aim of the ban is to curb plastic pollution, since the single-use plastic harms terrestrial and aquatic ecosystem very badly. The regulations are gaining momentum across the globe. In Europe and other regions, targets are already being declared for use of recycled content in packaging. In Europe alone, there are packaging and packaging waste directives, circular economy packages, single-use plastic directives, EU plastic waste charge, and country-specific plastic packaging taxes, etc. Talking about India, 2018 plastic waste rules emphasize sub 50 micron plastic ban, phasing out the multi-layered packaging and extended producer responsibility for the producers and importers and all the brand owners. The National Resource Efficiency Policy 2019, it targets 100% recycling and reuse of the PET plastic by 2025. By the way, India is leading in the PET recycling. The rate we recycle PET right now is very close to 90% or more than 90%, and that itself is a record in the world. But then we are targeting 100% recycling in next 3 years. They say 75% of the recycling and reuse rate of other plastic packaging materials by 2030 in India. And the policy also talks about banning the disposal of recyclable waste to landfills by 2025. So all this, why we are talking about, all the policy and the global measures, because it is high time we need to rethink about the plastic, how to use the plastic. Our relationship with plastic needs rethinking. Plastics are versatile material, but the way we use them is incredibly wasteful. We take oil and gas from the earth to make plastic products that are often designed to be used only once, and then we throw them away. This is what we call a linear take, make, and waste model. Year on year, millions of tons of plastic worth billions of dollars ends up into landfills, burned or leaked into the environment. A staggering 8 million tons of leaks into the ocean every year, and that number is rising every day. The ocean is expected to contain 1 ton of plastic for every 3 tons of fish as on 2025. If we don't rethink about the plastic reuse, there will be more plastic in the ocean than the fish itself by 2050. Plastic use has increased 20-fold in the past half century and is expected to double again in the next 20 years. No one wants to be in this position, we know. Is it possible to rethink the way we design, use, and reuse the plastic to create a circular economy? Let's see. Plastics, is it a blessing or a trouble? Yeah. So today, imaging a world without plastic, that is nearly impossible. Plastic are increasingly used across the economy, serving as a key enabler for sectors as diverse as packaging, construction, transportation, and healthcare and electronics. Plastic now make roughly around 15% of the car by weight, and about 50% of the Boeing Dreamliner is plastic. Plastic have brought massive economic benefits to these sectors, thanks to the combination of low cost, versatility, durability, high strength to weight ratio. So plastic production is expected to double again in 20 years, there is no surprise, and almost quadruple by 20 and 50. It is going to increase, that is what we want to say here. The United States, Europe, and Asia jointly account for 85% of the plastic production in use. So here we can see this data I have captured from the global plastic production. So in 1950, the global consumption was around 2 million metric ton. Today, after almost 70 years, we are using 460 million metric ton. So that is at 230 times in last 70 years, and it is expanding day by day. So plastic is now part of our modern life and cannot be banned. We must manage the way we use. Okay, so plastic waste is a trouble. Plastic itself, probably a question, is not a trouble. So before we move ahead, I just want to bring everybody on the platform to understand what is plastic. So basically, when we use item on the right side, I want you to see on the logo. So whatever plastic item we use, you might have seen this symbol, this kind of symbol. So this symbol is indicating what kind of plastic the article is made of. So if you see 1, it is basically polyethylene terephthalate PET. If you see 02, it is basically polyethylene high density. If you see 03, polyvinyl chloride. If you see PELD, that is 04, that is low density polyethylene. Polypropylene is 05, and 06 is basically polystyrene. 07 is miscellaneous, other than this, that is what the symbol means. So basically, these are all the plastics, and the applications are listed here. The actual status of recycling. So if we see that, very commonly recycled is PET. I talked about that 90% of the PET in India is being recycled, and that figure is much more than anybody doing in the world. Very commonly recycled is high density polyethylene. PVC is also being recycled, but not very common. LD, sometimes it is being recycled. Polypropylene, commonly recycled. Yeah, so these are all part of the polyolefins, and they are basically very friendly for recycling. Let's understand the plastic footprints. So currently, strong growth of plastic usage continues as expected. The plastic sector will account for 20% of the total oil consumption and 15% of the global annual carbon budget by 2050. And this is the budget that must be added in order to achieve the internationally accepted goal to remain below 2 degrees centigrade increase in the global warming. I believe all of us know that there is a international target to remain below 2 degrees centigrade global warming before 2050, and there are some norms. This is one of it. Even though plastic can bring resource efficiency gain during the use, these figures show that it is crucial to address the downside of plastic usage, and circularity is the real answer. So as we can see here, basically recycled plastic is around 9%. Going to the nature environment is 80%, 11% in the incineration. So this 80%, which is a leakage to the environment in the ocean, in the Mother Earth nature, is a concern, and that is what we are talking about. As on today, 8.3 billion tons of plastic is already produced, and it is present on the earth. Flexible packaging is almost uniformly single use, and it is the most challenging segment, consisting of almost 30% of the total use of plastic. If the current production and waste management trend continues, then roughly 12 billion ton of plastic waste will be either landfilled or in the nature environment by 2050. So we talked about 80% leakage, from the 8.3 billion, and it amounts to 6.5 billion metric ton, which is leaking to the environment. So basically, the way we use plastic today is a kind of linear model, and I will explain here why we call it linear. So as we talked about, our relationship with plastic needs rethinking, right? Plastic are versatile material, but the way we use them is incredibly wasteful. The use of plastic has increased in last 50 years, and the material has many benefits, but now we know the negative consequences, and it becomes the waste to the pollution. So what we do, we take oil and gas from the earth, right? So this I have shown, the oil exploration, and basically this is converted to the plastic. So we have downstream petrochemical and we convert it to the plastic. So the plastic products that are often designed to be used only once, and then we throw them away. And this is what we call it, the linear take, make, and waste model. While the material has many benefits, but we know there are negatives, consequences, and we need to avoid that. So here I try to show, the upstream, which is oil exploration, feedstock production, and polymerization. Then you go to the midstream, and that talks about the manufacturing of intermediate plastic components and articles, manufacturing of the final assembled packaging, manufacture and consumption of the product. And the downstream, basically it is talking about the disposal and end use treatment. So use of plastic products and packaging, waste collection and sorting, then it goes to the recycling or either reutilization. So this is the way, we can see the life cycle of the plastic, and it is more or less linear from start to the end. Now let us talk the linear flow of plastic and how it is distributed. Yeah. So we can see here, virgin feedstock, then we have the polymer production, then we have durable application, the value creation. So out of the total plastic, here we can see 25% is incinerated, 40% is going to the landfill, 19% is going to unmanaged dumping or the leakage to the environment. So most plastic packaging is used once. 14% is collected for recycling, and 95% value of the plastic packaging material, which is worth US dollar around 80 to 120 billion annually, is lost to the economy. So how can we design a circular economy for plastic in which it never becomes a waste or pollution? That is what we want to understand today. So basically here what I want to say is, without any fundamental redesign and innovation in the system, about 30% of the plastic packaging will never be able to be reutilized or reused. So this talks about the full spectrum of plastic usage in India. So we talked about, the global consumption and scenario and how the statistics are. Now this is about India. So India, basically we have the, per capita polymer consumption of 16.8 kg per person. And that is much, much lesser than the, the consumption of some of the advanced country like America or Europe, or even we compare with China, we are half of that. And we are still, around or lower than the global consumption. So basically, I want to, indicate here that there is a potential chance for growth ahead. So out of this, polypropylene is 4.54 kg per person, LLDP, SDP, PVC, and so on. So PP and PE segment is the largest one, right? And basically, I'm talking about the polyolefins here. It comes to around, less than 15. And finally, it goes into the the cycle of use, manufacturing and all, and it goes as a waste. So packaging and plastic waste, 3.67 is being recycled. Yeah, 0.79 is used for energy conversion, and packaging of plastic waste litter dumped, openly burnt is around 2.8 kg per person in India. Packaging plastic circulation is 1.81. So this gives us, kind of picture that where we are using the plastic and where the opportunities are still available. So we understood the linear model of the plastic, yeah, starting from the oil exploration, the way we manufacture, the way we use them and destroy them. Now, let's talk about the circularity. So what is circularity? So circularity means a product is created with its own end of the life considerations. In a circular economy, once the usage of the product or material is finished, it goes back into the supply chain again instead of routing as a waste or the disposal. So we can see here, so we start with monomer, it goes for polymerization, becomes polymer. So finally you have the product for use. And this product, once the life cycle is, completed, then it again converted to monomer. Yeah, the other alternate is it goes for repurposing process. You recycle back to produce the article. So this is what is the circularity. So rethinking the way we make, use and reuse the plastic is basically circularity. The systematic approach to create a system that practically works without loss of any economic value. No plastic waste or pollution. So I would like to put here the famous quote of United Nations Brundtland Commission. Meeting the needs of the present without compromising the ability of future generation to meet their needs. And this is what the motto of circularity. So how can we design a circular economy for plastic in which it never becomes waste or pollution? In order to do that, what we need to do? So there are some vision points which will help us realize the circularity. So there are two vision points I want to highlight here. Basically, design which is focused and fit for the circularity system. It has basically three elements. All the plastic packaging is either reused, recycled, or composted in practice. Elimination of problematic plastic packaging through new innovations. Reduce the need of single-use plastic, reusable models. The second vision point is plastic should be free from hazardous substance. Health and safety should be respected. So when we manufacture plastic, there are many chemicals, ingredients, additives we put into that. Some of them are quite hazardous even at a trace level, ppm or ppb level. So this kind of plastic, when it goes into the system, recycling it or getting it back into the circularity is a challenge. So this challenge should be mitigated by putting the ingredients with rationality. So the key concept here of the circularity is to decouple the plastic from the fossil feedstock. We don't want to use the oil explored from the earth. We want to have the alternate means to make plastic. So there is a foundation or organization very famous across the globe is Alliance to End Plastic Waste. So Alliance to End Plastic is a mission for better management of plastic waste through collaboration and collective action such that this complex problem can be solved. The members are some of the global conglomerates. So we can see here there are around 70 big brands coming under the umbrella of Alliance to End Plastic Waste. The members are committed to act. They invest through funding, expertise, and resource to enable the vision. They work to demonstrate projects and programs that create and extract value, proving the investment market from plastic waste. So these big brands are basically working together, kind of alliance to exchange the know-how, to exchange the fund investments and all, to make the world better by way of better managing the plastic waste. So together to end the plastic, I mean, these are the members we talked about, and I tried to put here the mission of this alliance to end plastic waste, and it talks about better management of the plastic. So with this, I think we talked about the statistics around plastic, how we use that, and how we want to see the future usage. And if we don't do that, what we are going to see down the road. So from now onwards, my friend Manoj will take it over, for the rest of the presentation, and he will talk about the conversion process and circularity. So Manoj, please take over.
Thank you very much, Manish. Let me share my screen. I hope it is visible.
Yes, it is perfectly visible, Manish. Yes.
So Manish, thank you very much. I think Manish has elaborated at length that he has built the background. Why we are talking of all this circularity and all, why it is needed. See, the problem is really very big, but at the same time, there are a lot of efforts have started already in this direction, and we are in correct direction. So just I will start from where Manish has talked. I will talk of options. We know the problems. Oceans are flooded with the waste. There are big heaps everywhere of plastic waste. What are the solutions then? So currently, if you see in this slide, cracker plants are producing monomers. Polymer plants use them to make plastics. Packaging manufacturers, they make articles. Brand owners use this, say, packaging material. Consumers are consuming them. Finally, it is ending up as a waste. We know majority of it is a single use. So either it is collected, sorted as it should be, but many times it goes to, say, landfilling or unknown sources, ends up in environment. The waste which is known, whatever we know, some portion is going to mechanical recycling, which is very small portion. Currently, I will say it is not more than 10 to 15%. Manish, I think he has shown a lot of statistics, but on overall, it is not more than 10 to 15% mechanical recycling. Majority is going to either landfill or energy recovery, or sometimes it is incinerated without any energy recoveries. Really, it is a big wastage. It is costing the world a lot. So now new ways are emerging up. Although mechanical recycling is very big option and it will continue in near future. We'll talk on all options at length, but there are new ways are emerging which are called advanced technological solutions or advanced recycling. One is dissolution. You can see on my slides. Then chemical depolymerization and pyrolysis. There is one more option, gasification. I'm not covering that, which is, say, newly emerging, but these three are, say, they're going ahead a really strong way. We'll talk of these three solutions in detail. First of all, this mechanical recycling, which is a traditional way. Traditionally and most widely used is the mechanical recycling, which is physically without affecting chemically. We're collecting the plastic waste, collection. So it is sorted, shredded, like size reduction of the articles to make it homogenized, washed, and then again new articles are fabricated, either by extrusion or any other mechanical operation. It is just basically it is combining all plastic waste mechanically and making new articles. Points to be noted, like what are the disadvantages of doing this? This is very easy. Mechanical recycling is the easiest one. But material is getting degraded. everyone might have heard this, say second-hand plastic or second-grade plastic. This is nothing but recycled plastic. Its quality will not be similar to the virgin plastic or new articles. So quality would be inferior. Although its chemical structure is not changed, it is same polymer, but it is a mixture. And with every recycling, it will get degraded. So it is not a good way, but currently this is the only prevailing way. Around 10 to 15% of plastic waste is being recycled in mechanically. And for foreseeable future, we'll talk of this also in detail. For foreseeable future, it will be in practice. I will show you the new age in the next slide. We will go to other solutions, new age solutions. So we spoke of dissolution, depolymerization, pyrolysis. So first of all, what is dissolution? Dissolution is a mechanism which is solvent based. It uses some proprietary solvent which dissolves the plastic waste, and it is selective to plastics only. And there are so many other things like additives, resins, or inks for that matter, that will get segregated, and you will have only pure plastics going to solution. So main product would be polymer. It would be pure polymers. So it is expected that, like, it is targeting, solvent would be targeted to either PE, PP, PVC. If it is mixture, then it will be a mixed polymer, which will be of no use. So it is a targeted methodology. Dissolution should be applied on targeted polymer. Chemical agent needed is a solvent. Solvents, there are few front runners. They have their own proprietary solvents. Temperature would be around 990 to 280 degrees. This is the temperature range, not very high. Other methods which we'll be describing with temperature requirements are very high. Comparatively, this has, say, lower temperature requirement. Pressure also reasonably okay, 1 to 5 bar pressure. This method has a lot of advantages, and there are few front runners like Creosol and new cycling. Creosol is invented and marketed by Fraunhofer, new cycling by APK. Maybe many of us might have heard Creosol because Hindustan Unilever or globally Unilever, they have tied up with Creosol, and these sachets, everyone like sees this shampoo sachet or sometimes hair oil. Many things are coming in sachet, small ticket items. So this is big problem for recycling because there is some chemical left out, or chemical or whatever material. So shampoo, how to recycle it is a headache. So this Creosol, Unilever has tied up, and they will be recycling using this method, Creosol. Currently, annually, there are hundreds of billions of pouches are generated. So it is expected Creosol will be of great help, and it will be making this life easy for recycling this sachet, or for that matter, any other targeted polymers. Now let's go to second method, which is depolymerization. Depolymerization is nothing but reverse of polymerization. The technique finally from polymers will be again going back to monomers. So how they do it? Feedstock is high purity polymers like PET. This method, by the way, is mostly successful on PET and polystyrene also. So for PET, if you take PET bottles or PET mixture, finally you will be making monomers and oligomers like terephthalic acid and glycol, monoethylene glycol. That would be the products. So these are the monomers from where PET was made. So this process would be reversing it to make it again the monomers. Chemical agents are solvents as well as some enzymes, or it can be thermal also. For this method also, temperature requirement is not very high. It is 80 to 280, which is reasonably low temperatures. Pressure requirements 1 to 40 bar. So Ionica is the front runner. Ionica, GR3N and Agilix. These are the players in market currently. They invented some processes, and now they have commercialized also. So this method is majoritarily it is in use for PET. Next is pyrolysis. So pyrolysis is the most promising. I will explain you some more details about pyrolysis, why it is so promising. So mechanism of pyrolysis is thermochemical. It is thermochemical. It is decomposes the material in thermochemical using thermochemical technique, and in the absence of oxygen. So in anaerobic environment, it thermochemically decomposes the material. Feedstock would be mixed plastics. Good part of this technique is it can handle any mixture. Like the first method, dissolution, it is focusing on targeted polymers, while pyrolysis is tolerant enough to handle the mixture. Main product would be oil hydrocarbons. By doing pyrolysis, we'll finally getting the oils. These oils would be a mixture of hydrocarbons, which can become a feed for petrochemicals like crackers. No chemical agents are needed. Temperature requirements are slightly higher, 300 to 600, because it is thermochemical process and decomposition. 300 to 600 degrees is the requirement. Pressure is low, 1 bar, no high pressure is required. There are so many players in this market. Nexus Circular, Blue Alp, Prime, Plastic Energy. These are the big names of this field. Brightmark, Carbolic, Agilix. They have their own processes. They have researched, and now they are scaling up the processes. Because everyone is sensing there is a big opportunity in this market, because by regulations we saw a lot of regulations which will be forcing us to go in this direction. Recycle will become mandatory. So pyrolysis will be the big solution nowadays or going forward. So I'll take up some more details about pyrolysis process. Pyrolysis can convert low sorted mixed plastic waste to cracker feedstock. As I said, there is no compulsion to have, say, segregated like polythene, polypropylene, PVC. If it is a mixture, then also it is okay, because it is not segregating polymer wise. It is doing decomposition of in entirety. So that is the most favorable part of this technique. That's why it has a lot of potential, because sorting is a big headache for recyclers. It is not easy task. So if any process is tolerant to mixture, I think it is going to be very successful and popular. This process has potential to boost recycling yields. Recycled yields are very, very good. It has potential to meet vision of plastic circular economy model. This process can be scaled up, and currently, although we have sizes of say 30,000 tons per annum or so, but they are under scale up, and like we saw for earlier, maybe in 90s, we saw scale up in petrochemical crackers. Earlier crackers used to be of very low capacity. Nowadays, you have more than 1 million tons capacity. So experts are expecting same will happen with pyrolysis process, and will have scale up very soon. It also depends on demand. So see, there are a lot of people researching. So this is one of the research laboratory, Ghent University's LCT. They have researched, this is a few years back, they have developed this process together with others. In simplified form, I will describe this. So plastic waste post-consumer, the mixture will be extruded. To make a, say, extruded mixture, that would be sent to reactor, where there is this thermochemical process will happen, decomposition will happen, and then there will be a condensation section. This is very, very simplified, although plants will have, say, a lot of sections to handle it easily. But in simplified form, it would be 3 phases. And result would be liquid product. You can see the black bottle. It would be black liquid like this. Okay, so if you see gas chromatography or some advanced analytical techniques, this is what you will get up when you inject this mixture. It would be naphthenoaromatics, monoaromatics, diaromatics, and also majority of it is paraffins, isoparaffins, olefins. And people who are familiar with petrochemicals or crackers, they know this is useful for cracker plants. So this is where the beauty of this process. Finally, it converts waste polymers into this useful. You can see these blue waves on gas chromatograph. These are the useful products. I will show these details with what is the composition. So composition, there are three main categories. You will have useful compounds like hydrocarbons, which are similar to cracker feeds, which yield good amount of propylene and ethylene. Some non-useful compounds, heavy olefinic aromatic compounds that yield heavy fuels. And also there will be contaminants or heavy oils. These contaminants and heavy oil, they pose big risk to cracker operations. So currently this is also a challenge for researchers. A lot of work is going on, and we are hopeful, like experts are also hopeful, they will find some way. If you see composition in details, if you see carbon number range is mixed pyrolysis oil. MPO means mixed pyrolysis oil because we are feeding mixture to this process. So carbon number range wise C5 to C51, this would be the range of carbons. So by C51 we know it is very, very heavy carbon. So it is a, say, viscous mixture. It will have around 41% paraffins, 40% olefins, naphthenes 11%, and aromatics 8%. Although when you compare it with fossil naphtha, which is a good cracker feed, which has composition up to C9 components, C4 to C9, and normally it has 79% of paraffins. So cracker persons know the 70 to 80% paraffins, or even more than 70, anything more than 70 is good feedstock for petrochemicals. Although this MPO has 41% paraffins, but it has some olefins also. I will show you some yields also, what it makes. If you see the column in between, which is PE film, it is made from, when PE film only is fed to this process, what it will make. So it is also almost similar. Say paraffin 37%, but it has high olefins, naphthenes and aromatics. But practically you are not going to get this separate mixture. What we get from market as a waste would be mixture. So this MPO is more relevant. We'll see in details what we make by this process. First of all, let me talk of integration, how this process can be integrated with cracker plants. I'm sure many of us would be familiar with cracker plants. Let me very simplify what cracker is. Cracker has basically two main parts. One is furnace part and other is separation section. Although cracker is very complex, it is not that simple, but basically even for lemon, there are two main parts, furnaces and separation section, which has a lot of processes like compression, drying, reactions and distillations. So I'm calling it combinedly as a separations. So the process which we are talking of, pyrolysis, is, my cursor is rolling on that, this plastic waste after sorting, which is going into this green. So this green part with liquid products, this is the pyrolysis part. So let me start with consumers, where we ended when we were talking of plastic waste. So waste from consumers, plastic waste, which is after sorting. After sorting means you will not be sorting the polymers, but at least glass, wood, metals, this need to be sorted. So only mixture of polymers to be fed. This mixture is fed to this process, which is thermochemical, as we talk of, and the liquid, black liquid. Now, as we said, it has a lot of contaminants also, so it needs to be first purified. After purification, it will be fed to furnaces. This material currently, whatever product we get from this pyrolysis process is so viscous, cannot be fed alone, also because of contaminants. So plan is currently to mix it with current feeds of furnaces like naphtha. If for naphtha furnaces, you can take 95% naphtha and you can mix 5% this new liquid, which is pyroil. It is fed to furnaces, and then similar to normal cracker, separations. I talk of one more process, gasification, which is currently not in big limelight. It is still under development, but work is going on. That process will be gasification, which will produce gas product. So if that process is in use in future, that will be making gas. So gas purification is needed, and that gas can be directly fed to separation section of cracker. Finally, what cracker plants will be making out of all this is ethylene, propylene, butadiene. These are the regular cracker products. So again, this is the monomer for polymer plant. So it is joining this chain of feed to polymer plants. Polymer plants are making polymers, which is going to consumer. This is how finally we can see this circle is being closed. Waste coming to crackers, monomers, polymers, and consumers. So this cycle is getting closed. So in future, experts are hopeful, researchers are working that this proportion can be increased, and slowly this will be large proportion of cracker feed, and it will give opportunity to reduce the fossil feedstock, which is naphtha, or let us say gas feedstocks. We'll talk further on yields. This mixed pyrolysis, repeatedly I mentioned, it would be mixture. What it will make, like what cracker will make out of cracking this mixture. So research and also some small commercial plants are nowadays running. So the analysis shows that it is making around 25% ethylene. Cracking of mixed pyrolysis oil, it's making 25% ethylene, which is reasonably good. Earlier, it was not expected that there will be good ethylene yields, but this is the outcome now. Compare it with reference feed, which is naphtha for crackers, which is yielding around 30.1%. It's typical at 850 degrees COT of furnaces, you get around 30.1% of naphtha, 30.1% of ethylene from naphtha. Comparatively, this process, mixed pyrolysis oil would be getting around 25, which is not, say, very bad. Also, it will be making other products like propylene around 15%. Total C1 to C4 components would be 69%, which is a very, very good proportion. And because of its heavy nature, there will be pyrolysis gasoline also and pyrolysis fuel oil. So picture is not as rosy, although we are seeing good things, but disposing this heavy feedstock, processing this heavy feedstock is a challenge. And disposing this heavy mixture also would be a challenge. This is more viscous than CBFS made in cracker. But small proportions, currently there is no issue. Challenge would be there when the proportion is increased. There are some more challenges, like, as I said, mixed pyrolysis oil is very heavy. So cracker furnaces, people familiar with furnaces know, convection section will have challenge of fouling when heavy feed is processed in furnaces. Yeah. Let me share with you some examples what giants are doing. There are Manish shared, there is alliance for ending the plastic waste. So what giants are doing in this field? So let me share you the example of Shell. Shell has collaborated with Nexus Fuels, Blue Alp, and Prime. Also, Shell has invested in Blue Alp. It is a joint venture. They are supporting startups and invested a good amount so that these new options come up. So what they are doing, they have developed different methods to reprocess this plastic waste, converting into cracker feed. So Shell is supporting. Shell has offered them, they themselves would be processing this material in their crackers. So already Shell has started these trials. They are targeting by 2025. So from 3 years from now, Shell would be reprocessing 1 million ton total. They are targeting total 1 million ton of reprocessing in next 3 years. If you compare current solutions, maximum available capacity which is under construction is 100,000 tons, which is 1 lakh ton. So this is big amount. Shell has taken a big challenge. SABIC, the big name in petrochemicals, SABIC and Plastic Energy, which is a one startup which has now grown in a big way. They also have joined hands. They will be producing tech oil, which is nothing but a thermally cracked oil, which is a feedstock. They'll be using this feedstock for their plants. Some more examples: Total, French company. They have joined hands with Recycling Technologies, which is also a new company, new age company in research and developing new technologies to process plastic waste. They will be producing flax oil using this thermochemical process, thermocracking process. More names: BSF. BSF has developed solutions for purification of pyrolysis oil and gas. See, as I mentioned, the pyrolysis oil has a lot of contaminants. So someone has to work on purification. So BSF, which is a well-known chemical solutions company, they are developing solutions for easy processing of this pyrolysis oil and gas. Finally, which will allow this scale up and continuous processing in crackers. I shared example of Unilever. Unilever, they are using Creosol process. They also funded this research process, and now they will be using sachet recycling technology from Creosol for recycling the sachets. So these are just some examples. There is a lot of work going on. So many companies are, say, voluntarily coming forward. They are donating, but more than that, they are coming forward to try themselves. They are offering their plant. It is also a big support that someone like Shell or Borealis, they are offering their plants. Okay, you can do research, because finally without research, you cannot scale up. So that is also a big contribution. So these all are, whatever I mentioned, they are members of Alliance to End Plastic Waste, and they are contributing a big way. Let us move forward. There are a lot of challenges. Path is not easy. Many times I said. The first challenge, it is the variability. Plastic waste, if you see geography, it is, even in India, if you see region-wise, there is a lot of variety. Like some places there is a lot of polypropylene generated, some places polyethylene. Demography-wise, South India, North India, East India, a lot of variety. If you see countries, so North US, North America, South America, Africa, Asian countries, there is a lot of variety. Plastic waste generated country-wise is not same. Like in India, everything is ending up in waste. At least in Europe and US, there are some recycle methods of developed. So waste composition is slightly different than what it is generated in India. But this variability is a big problem in processing. So quality of these products depend on this waste generated, and which is differing, as I mentioned. Second challenge is contaminants. This is a big challenge. Peroxides, carbonyls, NOx, metals, chlorides. You name any contaminant known to chemical plants or petrochemical plants or crackers. Whatever we thought of in any past or future, everything is present in pyrolysis oil. All the contaminants you name, it is present in pyrolysis oil. So there are techniques required to purify this first before you can put to crackers, because cracker plants are like elephants. Turnarounds every 4 to 5 years. They are not say shut down regularly. Every startup and shutdown is a big thing. Even if any contaminants is forcing plant to operate on low load, it is a penalty in millions. So no one would like to do that. So purification is needed. So these contaminants, research is going on. Technology licensor like Technip, Linde, they are all working on making the solutions or implementing the solutions, how safely this pyrolysis oil or pyrolysis gas can be processed in crackers. So purification is very necessary. Third challenge is economics. Although we found solutions, like let us say BSF working on purification, Technip, Linde, Lemas, all are working. They implement, but still this purification process, or for that matter, plastic recycling, it's not going to be cheap. So many steps are involved. It would be very cost expensive affair. So if you see from cost competitive point of view, cannot sustain. Currently, there are whatever techniques, or even if you see 5 years down the line, whatever research is going on, it will not be yielding any cost-effective solution. Currently, feasibility, the target is feasibility, cost is secondary. So economically, it is going to be expensive. So also, these people, whoever are working in this field, governments are supporting. Also, this fund, Alliance to End Plastic Waste, they are also contributing for research, for developing this. But still, some governments, not in India, because India is very cost sensitive, but some governments, they are subsidizing the green product. Like some governments are making it mandatory. Some proportion of plastic must be recycled plastic. Or every cracker plant must process some, say 2%, 5%. It is going to be mandatory going forward. Fourth challenge is scale. So currently, I mentioned there is some 30,000, 40,000 tons per annum capacities are already started, and some facilities under construction have 100,000, which is in India we call 1 lakh. So 1 lakh tons capacity is under construction, but still this capacity is not very high compared to the waste which is getting accumulated. The annual waste figures, if you see, the numbers are very, very high. Let me put some figures. In 2040, people are talking of 460 million tons plastic waste. 460 million tons, and currently we have processing capacity of 100,000 tons, which is very small. So everyone is hoping of scaling up. Current scale is not very high. Even if plants are scaled up, collection, sorting, reprocessing, these facilities are still not scaled up. So anyway, work is going on, but currently this is a challenge. One more challenge is sorting. Current sorting facility is inefficient, expensive, and time consuming. You see the geographies, wastes are collected at one place, processing plant would be at different place, and also it is very bulky. So somewhere it would be, say, compressed or size minimized. It's going to be a big affair. Currently it is very inefficient, but research is going on. So again, I will say there are a lot of challenges, but work is going on, and people are hopeful that next 2 to 3 years we will have big breakthrough and capacity increase in this field. Coming to opportunities. See, opportunities, by 2040, we will have 420 million tons of plastic waste generation. And now at current moment, there is no chemical route, or let us say very less than 1% plastic waste is recycled on the chemical route. But with this all research, let us hope that in next, say, 15 to 20 years, will be around 20% recycling by this route. So it is ending up at 88 million tons. Out of this, if pyrolysis method is applied to 75%, it is also 63 million tons. So if I apply 100,000 tons of plant which is under construction, we will still be needing around 600 pyrolysis units globally, which is a huge, huge market. So that's why I'm saying it is, say, at the same time, where if there is some challenges, this is my big opportunity also. So all researchers are looking on this opportunity. This is opportunity to enter the first mover market, first mover advantage. So licensors, technology licensors, or let us say researchers or startups, they want to be first mover. People are putting up new capacities because big boom is expected. This is a big opportunity. I also tried to estimate how much ethylene we expect from this. Even if 63 million tons of pyrolysis oil is processed in crackers, 13 million tons is going to be ethylene, which would be 4% of capacity that time. Although it would not be big, very big, but you see the 88 million tons, it has accommodated 88 million tons of waste. That is important. Economically also, it is big opportunity. Like last year, assumption was it is 40 billion, around $40 billion was the market of global plastic recycling. And one agency, Transparency Market Research, they have estimated a very conservative rate of increase, CAGR of 7%. So they're estimating it would be around $80 billion market by 10 years. Not small by any means. Yeah. Okay, let us move forward. So I'm coming to almost end. Key takeaways from whatever we heard from Manish and whatever I presented. First takeaway is meeting sustainability and regulatory goals is going to be challenging. It's not easy. And it will need metrics of plastic recycling solutions. Whatever solutions we have discussed today, all solutions would be needed. And I'm sure there is research going on and more would be added up to this list. Second takeaway is mechanical recycling. Mechanical recycling, currently it is, and it will remain a key process for large quantities, at least for foreseeable future. Although it has its own disadvantages, but still it is the easiest and cost effective. So in countries like India, it is still the biggest way. It will remain biggest way for foreseeable future. Pyrolysis, which I spoke at length, it has very high potential, and it will have always edge over other advanced recycling techniques in handling the bulk of mixed plastic waste. Basically, its advantage lies in this mixed. Sorting is very difficult, so pyrolysis has big advantage of this mixed handling, ability to handle mixed plastic. Fourth takeaway is big investments are needed in waste collection as well as sorting for supporting recycling ecosystem. Whatever targets governments are putting or regulators are putting, or even this conference which has just ended, COP27 in Egypt, I think you must be aware, there is Paris Agreement. They have put very ambitious targets by 2030, 2040, and there are a lot of targets for 2050 also. To achieve these goals, we will need big investments. It's not going to be easy, but already trend has started and the trend is promising. Plastic recycling route will not remove the need of fossil fuel. See, many people are talking of that it will be fully, cracker plants would be fully operating in plastic waste. So experts are not seeing this possibility for say coming 15 to 20 years because it is very, very difficult to replace completely. At least it would be scaled up and it will make a good proportion of cracker feedstocks. Fossil feedstock, if you want to replace, then it has to move on bio-based fuels, bio-based feedstocks. Then only you can completely replace fossil fuels. Plastic waste recycling can make significant portion. That is what I can say. Finally, I end this with a good sentence from Mahatma Gandhi. The future depends on what we do in the present. All actions we are doing in currently 2022, it is going to decide this future, 2030, 2040, time of our next generations. Lastly, disclaimer from our side, from myself and Manish, that this presentation is solely to share knowledge. It not necessarily offer any suggestions or advice. And it is information based on our experience, also on literature. We are not claiming any copyright. Copyrights lie with their owners. Thank you. If you have any questions, you can type on question and answer session. Panchal sir, I hand over back to you. Sir, you are muted. Panchal sir. Professor Panchal, you are muted.
Thank you, Manoj ji. Thanks for a very nice collaborative session. Thank you, Manish ji. Here we have one question from one participant. Any of you can please answer. The question is, how can we minimize segregation of waste plastic blended with bitumen through wet process?
Yeah, so I see this question is from Mr. Chaudhary, right?
Yeah, Venkaya Chaudhary.
Yeah, correct. So basically, probably I will need some more information to understand, I mean, what is the source of the feedstock from where they are getting, such a plastic waste with bitumen. So probably, I mean, we'll be able to dig out further based on the feedstock, what kind of plastic he's talking about and what is the, so it is LDP and then LDP with bitumen, right?
Yeah.
Manish, it is very unique case. Bitumen blended with LDP. It's very, very unique case. Yes. I know of one solution which I think Reliance, they are intentionally mixing plastic into bitumen and other road making material. But segregation, Manish, you can share if you have anything.
Yeah. I mean, that is what, Manoj, I am also trying to understand. I mean, what the source is, because normally the plastic, which is, very low grade, not being able to utilize for any other upgraded purpose, there it goes to, the road making. I mean, blending
Correct.
bitumen and then it goes for the road making. That is what we have, seen so far.
I think Mr. Chaudhary also has written that it is used for road making. Yeah. So once it is used for road making, it is permanent. That's why it is used. That plastic waste you are putting on, say, roads, it is not required to again separate it. And if someone wants to separate it, it is going to be very tough. Very, very energy intensive.
Okay. So moving for next question, there is a participant, Hari Krishna B, is asking, can I start a pyrolysis process plant for recycling in India as a business?
Yes, sure. Actually, in India, people are slightly behind. In Europe, it has started a big way. I mentioned few examples. People have already started in Europe big way. So in India, I think some trends have started, but it is a big opportunity for India also, because India also has a big amount of plastic waste. Currently, it is going to landfills or some, say, incineration or less economically efficient ways. There is big future for pyrolysis process. So, Mr. Hari Krishna, you can surely think of this.
Yeah, thank you for your answer. The next question is, what are the prospects of having alternative to plastics in future? Or can we avoid plastic?
Manish, you can take up this.
Yes. So I think we talked a lot about it, right? The way plastic is involved in our life at present, right? And there are good reasons why the plastic is irreplaceable. So we have moved from the world of using metal, glass, and paper to the plastic. And at present also, there are many research which shows that when you use paper or metal, basically the use of resources is much in the tune of 2x to 3x compared to we use plastic. So I mean, basically, as on now, the way we see is the plastic is irreplaceable. What we need to do is proper management of the waste.
Right.
Okay, thank you. So let us move toward the end of the session. First of all, thank you, both the analyst, my eminent speaker, Mr. Manoj ji and Manish ji. I would like to invite Mr. Manoj at our IEI South Gujarat local center. Let's, Mr. Manish, kindly invite him once personally in our meeting. We will have a great interaction.
Yes, sure. Right.
Yeah.
Thank you very much.
Thank you. So moving toward the end of the session, our honorable president, Mr. Thakre sir, then Silpa ji and G Ranganath, they are involved in some other activities, so they have not been present during the entire session. My most valued invited panelist, Mr. Manish Joshi and Mr. Manoj ji, it's my privilege that I have been asked to give a vote of thanks on this occasion. Myself, Professor K.D. Panchal, obviously Honorable Secretary, IEI South Gujarat Local Center, Sub-Zonal Officer, Government of Gujarat. We have extend a very warm vote of thanks to all eminent speaker for gracing your important presentation. I must say, you must have given a very notable time period to create such a unique presentation. And I like the last slide, including Mahatma Gandhi ji, which spread a very good message to the participants also, and sharing with us your deep knowledge and opinions today. I may like to express my sincerest thanks to Thakre ji, Ranganath ji. Obviously, they are not present. Dr. Silpa ji, during the entire session, respected chairman of IEI South Gujarat Local Center, ladies and gentlemen. Once again, I want to state that we are all most grateful to my panelists on this stage. Last but not least, thank you, my all dear participants, for being with us this evening. It's a great pleasure. Thank you. Jai Bharat. Thank you.
Thank you very much.
Thank you very much. Thank you.
Okay.
Thank you.